Hi guys, welcome back to Business Statistics. Um, Sorry about the long hiatus, but I was sick, and yeah, that's basically it. So my voice might be a little bit raspy today, but I'm pretty sure we're gonna get through it. It was a lot worse a few days ago. Um, Pretty much done getting your test graded. I'm just still waiting on a few loose ends. I need to get some. Um, like work some of the scanned submission sheets turned in from some of the other students or from some students that haven't turned in the whole thing yet. And then I'll be looking at to see if there's a curve and all that kind of stuff and just finalizing and editing certain questions just to make sure that they're fair and all this stuff. There's a lot that actually goes into it. It's not just me looking at it, scoring it, and then just kind of blindly giving it to you. We kind of make a lot of decisions in the background about, like, given how this question was answered a lot, was it fair, blah, blah, blah. So a lot of that goes on, but yeah, I'm still waiting. Still waiting on some work from some students, and once I get that, then I'll be able to finalize the tests, get those back to you, and get all the scores submitted to Springboard so that you guys can kind of have an updated version of what your grades are. So that's that. Okay, so we have now concluded, I guess, Unit 1, we'll call it, in the Business Statistics course. That was half the chapters that we're going to cover, chapters 1 through 6. So now we've got 7 through 12 for Unit 2 and 3. Unit 2 is going to consist of 7, 8, and 9. And tonight I'm going to be putting out content on 7 and 8, as you can see on the screen. Yeah, without any further ado, let's get to talking about it. So chapter 7 and 8, as you can see, is sampling distributions, and confidence intervals. One thing that I want to kind of go back and talk about is what we have learned thus far and how that's going to prepare us for 7 and 8. So in chapter 1, we learned about data. That was a lot of review. That was a lot of stuff that you may have seen in perhaps a high school statistics course or just maybe in some other classes in general. Essentially essentially review and I guess easy learning. Chapter 2, there was some new stuff in chapter 2, but mainly review. We were looking at a lot of graphs. There was probably some graphs that you had never heard of. The Pareto chart comes to mind. It's kind of a mix of a histogram, a bar graph, and a cumulative line graph. So yeah, there was some new stuff in chapter 2, but mainly real easy, and we kind of coupled that with chapter 1. Chapter 3 was descriptive statistics. That was our mean, median, and mode, standard deviation, variance, coefficient of variation, that sort of stuff. That right now is going to be the stuff that you guys are at, like that's a tool set right now that you have from chapter 3 that you're able to use on the case currently. So hopefully you guys are taking advantage of this kind of downtime with me being sick, and hopefully you've communicated with your case groups. But the descriptive statistics portion is definitely what you could be doing on the case right now, is getting down just those descriptive statistics about pre and post scores for all the different categories, and then getting graphs to correspond with that, and talking a little bit about the skewness. But yeah, please let me know if you have any questions on the case. But yeah, chapter 3, definitely where it's at for where you can get started. I'd love to see you guys get a lot of that stuff done earlier rather than later, because you'll be chasing your tails by the end of the semester if you don't start that now. I promise you that. So I would love to answer any and all questions that you guys have. Just shoot me emails, put them in the discussion board, whatever. But yeah, I'd love to answer questions about that now. Yeah, and I'd love to help in any way possible. Chapter 4. Chapter 4, we got into probability. That was a difficult chapter. That's when the course really starts to ramp up, and we start to learn some tough concepts. We learned Bayes' theorem. We kind of said, hey, we're going to cover Bayes' theorem once, and then let's do it the easy way. Let's do it the way that we just throw everything into a contingency table, a probability contingency table, and then we answer questions by completing the table and then going from there. So that was chapter 4, and we learned all the rules of probability that are applicable for this course. So then we get into chapter 5 and 6. Chapter 5 and 6 were discrete and continuous probability distributions, and we learned discrete and continuous probability distributions. Amongst the discrete, we had just like the general discrete, which was, you have an x value and you have a p of x value, and the p of x values are associated with the x values, and those add to 1, and we calculate statistics based upon those. We also had the binomial distribution. We had the Poisson distribution. And I think that rounded it out for the discrete distributions. For the continuous distributions, we had the uniform distribution, which was the flat one. That was the rectangle. And then we had the normal distribution, which is going to be the most common thing that we roll with going forward here. And the thing that you need to understand the most is the normal. And then we also did the exponential, which I don't think we'll really see much in going forward in the course. But the main thing about chapters 5 and 6 is that we learned how to deal with probability distributions. Okay? And we learned how to kind of work in a universe that we have all of the information. We somehow have a data set, and we somehow know that the distribution of that data set happens to be normal, or it happens to be exponential, or it happens to be Poisson, or whatever. These are like mythical things. Like, this is not something that's ever really going to be the case. Like, if you know that, like, put it this way, if you know that much about a distribution or about a data set, like, why are you studying it? You kind of already know everything that you need to know. The reason that we cover those things is to kind of give you the thought processes and the skill set in order to be able to work with, or to think about the way that you need to be able to think moving forward, so that you kind of have an experience level in order to get into the stuff in 7 and 8. Okay? The stuff in 7 and 8 is sampling. And sampling distributions. All right, so we went through 5 and 6. We learned all these distributions in 5 and 6, but we did that so that we have like a general idea of what a probability distribution is and how we work with it. Okay, now in 7 and 8, we kind of relieve some of the constraints, and we say, okay, let's work in the real world. In the real world, we don't have all the rules defined for us. We don't just know that something is normal. We don't just know that something... we just don't just have all of the data elements of whatever we're working with. Or if we know that all of the data elements are countable, it might be just way too expensive to like run calculations on all the data. Like, imagine like if you were taking the census of the United States, and actually taking a true census where we're looking at every single piece of data. I mean, that would be absurd. You would literally have to survey, 290 million people. And there's no way that the information that you could glean from surveying them, honestly, on any number of topics, would be worth it given the cost of actually running that survey, right? So when they do the census, they actually take a fraction of that, like a small fraction of that, and then they interpret the results of that sampling and the statistics that they run on that sample in order to draw conclusions about the population, because it's more cost effective to do that that way. And it's, as we'll find in chapter 7 and 8, it's actually very you can glean very powerful and very accurate results based on a small number of data points relative to the size of a population. So we get to see this. I mean, this is election season right now, and you kind of see this in election season. You see all these different polls that come out about if Trump or Hillary is winning and whatnot. And these polls, amazingly enough, it's not like they've surveyed 10,000 people. A lot of the time they've surveyed 100 people. But they're able to garner fairly accurate results given the randomness of the survey and given the scientific method of the survey and the sampling. Okay, so that's kind of the point. So 7 and 8, we're kind of taking it into the real world. 5 and 6, we learned a skill set that we think is going to allow us to think in the way that we need to think for 7 and 8. And so now at 7 and 8, we're going to apply some of those, some of that thought process, learn some new tools, and figure out how we can adapt this to move forward. Random sampling. If we select n elements from a population in such a way that every set of n elements in the population has the same chance of being selected, then the elements we select are said to be a random sample. All right, that makes sense. So just we're selecting a number of elements from a population, and as long as each element has the same probability of being selected or the same likelihood of being selected, we call that a random sample. In order to select a random sample of n elements from a population, we make n random selections from the population, every element equal chance of being selected. Yeah, that's kind of what I said. Sample with or without replacement. With replacement, place the element chosen on any particular selection back into the population. We give this element a chance to be chosen on any succeeding selection. Okay, so that is as it sounds with replacement. You choose it, you put it back in the population, there's a chance that it gets chosen again. Without replacement, the exact opposite. So once it's chosen, it can no longer be chosen again. The best way to do this is to sample without replacement, because then we don't have any overlapping. Okay. And now we see that the types of sampling, we have probability sampling, convenience sampling, and judgment sampling. Probability sampling is where we know the chance that each element in the population will be included in the sample. This allows us for statistical inferences. Convenience sampling is where we select elements because they're easy or convenient to sample. So that's like volunteer response sampling. That's when the participants self-select. Okay, so you just use a customer service system, and then you get asked to do a survey at the end of the call. It is on you whether or not you want to respond to that. That's voluntary response sampling. So it's convenient. So as you can guess, the people that are going to respond to those samples are people who are just either really, really blown away with great service or just really, really ticked off with bad service. And then judgment sampling is where a knowledgeable person selects population elements. Judgment sampling is probably the most unreliable. We really want to be working with probability sampling in order to facilitate that randomness and in order to be making statistical inferences. 7.2, sampling distribution of the sample mean. Sampling distribution of the sample mean x bar is the probability distribution of the population of the sample means obtainable from all possible samples of n from a population of sample size big N. I'm going to go ahead and read this whole slide, and then I'll kind of explain what it means in layman's terms. In many situations, the distribution of the population of all possible sample means looks roughly like a normal curve. That's important. If the population is normally distributed, then for any sample size n, the population of all sample means is also normally distributed. The mean mu of x bar of the population of all sample means is equal to mu. The standard deviation sigma of x bar of the population of all sample means is less than sigma. Okay, so the standard deviation goes down when it's the standard deviation of x bar. Okay, so what does all that mean in real life? So we have a population of data points or population of elements, okay? And this is saying that rather than us worry about what probability distribution that population is, what we do is we sample it. With a number of data elements of little n. okay? And when we do that, say that there's 1,000 elements in the population, and say we sample it with 100 units because that's cost effective or whatever. Now, what we do is we create a new distribution. We no longer are thinking about like the elements of the original population data set as being our data points or as being our distribution, so the 1,000. We think of all of the possible sample means as our data points, right? So if we had n equal 100, there's going to be an X bar associated with that. There's going to be a sample mean associated with that. And we view that as our data point. We view that as our possible X bar in our new distribution. So no longer are we looking at a probability distribution that is about X. We're looking at a probability distribution that is about X bar. So we're looking at what are the possible sample means that we can glean out of this data set. The thing that's really, really important is what we get in these last two, okay? It's important to know that like this mu of X bar, this is an X bar for whatever reason, PowerPoint's not showing it correctly. But the mu of X bar is equal to mu, all right? So nothing changes in that regard, okay? But what's really, but that's a good thing. What's really important is that the standard deviation goes down. So sigma of X bar actually is going to be less than just regular old sigma. And so we get a more accurate depiction of what mu is going to be. Or when we sample and get an X bar, we actually get a more accurate depiction of what mu is likely to be. Okay, and when we sample, we assume that we really don't know what mu is. And so that's the whole point. We're trying to figure out, well, what's mu and how much confidence can we have in that? And you'll see that that's what we'll get into. I think it'll become more clear as we get into doing some problems, and that's, as you know, that's generally how I like to teach. I kind of leave it up to you guys, and I want you guys to then kind of climb in the book and read and all that stuff, and then ask me questions if you have questions. But I'm going to mainly facilitate a lot of the problem solving and then trying to explain the process through the problem solving in order to make it more understandable, because I know a lot of time when you read just this math jargon that it sometimes just doesn't compute automatically. So general conclusion, if the population of individual items is normal, then the population of all sample means is normal. Okay, so that's important to note. So if we know what the underlying distribution is, then we know that the population of sample means is normal. Even if the population of individual items is not normal, there are circumstances when the population of all sample means is normal. And this is what's really important. And this is why I said we're going to be using the normal distribution going forward in this class. That second line is huge because it's saying that like if we have a population of data points and they are exponentially distributed or Poisson distributed or uniformly distributed, that's that for that distribution, okay? But when we take a distribution of the sample means, assuming that we have a large enough sample, and we'll learn that going forward, assuming we have a large enough sample, the sample mean distribution tends to become normal, which makes it really easy because normal is one of the easiest distributions that we work with, and it's one of the easiest formulas, and we enjoy using the table because the table is fairly easy to use. Okay, so it makes it so that like, wow, now we don't have to like know this like whole plethora of distributions. We just have to sort of know normal, and then we take the sampling distribution, and then everything kind of just becomes normal. And it makes the problem solving a lot easier because we're not now looking at 5 different tables, we're looking at one table. All right, the mean of all possible sample means equals the population mean. We went through that in the last slide. That is mu is equal to mu of x bar. The standard deviation of sigma x bar of all sample means is less than the standard deviation of the population. Also in the last slide, that is yes and yes. Each sample mean averages out the high and low measurements and so are closer to mu than many of the individual population measurements. Okay, so that's important to note. When we're taking x bars, the highs and the lows are being averaged in, and so then this this sample mean distribution is not going to be as wide as the normal population distribution. It's going to be a lot skinnier because we're averaging a lot of the values. So these sample means are going to tend to gravitate toward mu. The empirical rule still holds. So within one standard deviation, man, I don't know why this is showing it like this, but yeah, this should be okay. It looks like I correct it in the following slides. Whenever you see sigma sub x or mu sub x, that's actually sigma sub x bar and mu sub x bar. Okay. For whatever reason, I must have missed that one, but I have it going forward. Okay, so yeah, the empirical rule holds. So if you recall the empirical rule from the last few chapters, that was within one standard deviation of the mean. We have roughly 68% of all of the data points. Within 2, roughly 95% of all the data points. And within 3, 99.73. Okay. Moving on, the properties of the sampling distribution of the sample mean. If the population being sampled is normal, then so is the sampling distribution of the sample mean. We went over that. The mean of the sampling distribution of x bar is mu sub x bar equal to mu. We went over that as well. Okay, and now this is where we get into some new formulas. The variance of which is sigma squared x bar of the sampling distribution is of x is sigma squared x bar is equal to sigma squared over n. Okay, and then the standard deviation follows suit as well. So sigma of x bar is equal to sigma over the square root of n. So that's just taking the square root of that whole variance formula. You take the square root of that whole variance formula, you get the standard deviation formula. Okay. So this kind of shows and proves that the variance of the sampling distribution, the sigma squared of x bar, is going to be less than sigma squared because we're dividing it out by n. Okay, so it's always going to hold true because we divide it out by the number of data points that we're taking in the sample size. Okay. Okay, and now we're going to get into confidence intervals. Confidence intervals is kind of why we do this. We're creating confidence intervals because we want to be able to adequately estimate mu with a high level of confidence. That's the layman's terms. So if we look at this, the probability that the confidence interval will not contain the population mu is denoted by alpha. So alpha is this new number that we're going to be talking about, and it's type 1 error. I don't generally refer to it as type 1 error, but I just wanted to mention it because that is what it is. Type 1 error, and then beta is type 2 error. We really don't get into beta in this class, but alpha is essentially the probability that we draw a conclusion and it's wrong. All right, so naturally we want that probability to be very, very low. Okay, so as you can see, when we do confidence intervals, we're going to be working with really, really small alphas. So then 1 minus an alpha that's small, so the probability that we're wrong essentially is going to be a large number. So we want a confidence level of, say, 95% or 99%. Those are actually going to be the two that we most commonly use in this course. So here's the formula. Okay, in general, the probability is 1 minus alpha that the population mean mu is contained in the interval. Okay, and the interval that we're looking at is x bar plus or minus z sub alpha over 2 times the square root of the sampling, or not the square root, the sigma of the sample mean. Okay, and that is to say, now we further expand that formula out and we say x bar plus or minus z of alpha over 2 okay, times sigma divided by the square root of n. So the only difference there is that sigma divided by the square root of n is that sigma x bar expanded, right? So sigma x bar right here is sigma over the square root of n. Okay, the normal points, z of alpha divided by 2 gives a right-hand tail area under the standard normal curve equal to alpha over 2. The normal point minus z alpha over 2 gives a left-hand tail area under the normal curve equal to alpha over 2. The area under the standard normal curve between negative z alpha over 2 and z alpha over 2 is 1 minus alpha. Okay, that sounds like a foreign language, but I'm going to draw a very simple picture that I think should make this more clear. Okay, so we have our standard normal curve. Let's pretend that that's symmetrical and normal and whatnot. Okay, so standard normal curve, something like that. Okay, and we want to come up, well, actually we're going to look at, we're not going to call that mu, we're going to call that x bar. And we want to eventually make a confidence interval, okay, with a certain alpha. Let's call alpha 0.05, okay, which means, this implies that we're going to have 95% confidence, right? So this 0.05 is the probability that we're wrong, 95% probability that we're right, okay? So we're going to have an interval, and we're going to chop off the ends. This first thing, so we're going to have a certain z value here. Z is equal to something, right? And then z is also equal to something right here. One is going to be the negative version, one's going to be the positive version. But when we know that the probability of being wrong is 0.05, we know that that's going to be on these tails. Okay, that's going to be out of our range. So our confidence area is right here. Our confidence interval is in here, right? It's this area right here. Okay, and so the probability of us being wrong, because it's symmetrical, is going to be 0.05, and so we're going to have 0.025 right here. So half of that 0.05 and 0.025 right here. Okay, so those are the different tails where we're wrong. Okay, and so then finding the z value is just going to be easy as finding either one of these points. If we could do it one of two ways. We could say, well, we know 0.025 is above this point right here in probability, so we just need to find the z value that I guess corresponds with 1 minus 0.025 or 0.975 in the standard normal curve, or because that would be our cumulative area under the curve. Or we could look on this side and find the z value that corresponds to 0.025. I think this one is easier because we have to do less thought. There's like less kind of logic that goes into it, and it's just like, well, we could just find the negative z value over here. So we're going to look in the table for 0.025. So we pull up our table, scroll down, and find our z table. We're on the left-hand side of it. We're on the negative side of it, which is a good thing. And now we want to look within the table in order to find a probability of 0.025. Okay, and we actually get very lucky because there is one that is exactly equal to it. I'm on this line right here, and we see 0.025 in here. And that corresponds to the z value of negative 1.96. Negative 1.96. So this is equal to negative 1.96. And by the rules that are given above here, we know that this is just going to be positive 1.96. But let's go ahead and check that, right? So we would actually be looking for the cumulative area So it would be the probability that Z, well, we'll just leave it at that. We're looking for 0.975 in the table. So we go here, now we go over to the positive side. And let's just check. Let's go over to 1.96. Boom. We have 0.9750 exactly. So it's perfectly on there. 1.96 is our positive Z. So that's that. That's how we find that Z value in our confidence interval formula. All right, so next thing we're going to do is we're going to start on our worksheet and we're going to solve some problems. Okay, so go ahead and turn to your worksheet. We're going to work on numbers 1, 2, and 3. Number 1. Business Week reports that its subscribers who plan to purchase a new vehicle plan to spend a mean of $27,100. Assume that the new vehicle price for the population of Business Week subscribers has a mu of 27,100. So that's an assumption that we're making. And a standard deviation of sigma equal to 5,200. What is the probability that the sample mean new vehicle price for a sample of 50 subscribers is within $1,000 of the population mean? Okay, so first let's calculate what sigma is, or what our sigma for our sample mean is. All right, what is the probability that the sample mean new vehicle price for a sample of 50 subscribers is within 1,000 of the population mean? Okay, so the first thing I'm going to do is I'm going to figure out what our sigma x bar is. And we know from our formula is that's just going to be sigma over the square root of n. Okay, which sigma is defined as 5,200. And then n is going to be the number of our sample. So square root of 50. And that is equal to 735.39. Okay, and then so essentially now we're just going to be taking a z-score and we're going to be running z-scores. Okay, so the first z-score, because it's saying we want to know if it's going to be within $1,000 of the population mean, or of the proposed population mean. Okay, so what are our two numbers for 1,000 between each population mean, or between the population mean? We're looking at 28,100, and we're also looking at 26,100, right? Those are numbers that are within 1,000 of each population mean. So we're just going to calculate z-scores based upon those. So z is equal to 28,100 minus 27,100 all over the sigma of x bar. So 735.39. Okay, and so that's that, and that gets us. So not surprisingly, the top of this is positive 1,000, right? Because that's like in the definition of the problem, essentially. Like, so it's going to be positive 1,000 over 735 plus 735.39. So this actually gets us a positive 1.36. And then, so not surprisingly, this 26,100 minus 27,100 is going to be a negative 1,000 on the top, divided by that same 735.39 gets us a negative 1.36. I'm going to go ahead and move this down. There's a little bit more room to work. There we are. Okay. All right. And then essentially now we're just going to be finding the probability that z is between those two. So realistically, we're looking at the probability that X is between 26,100 and 28,100, right? But we just calculated z-score so that we can actually use our table, and so then that's going to be equal to the probability that z is between negative 1.36 and positive 1.36, which we know that we do this by probability that z is less than 1.36 minus z is less than negative 1.36. I'm not going to explain how to do that because that's what we learned in Chapter 6. Okay. So from this point, I'm going to assume that everybody knows exactly how to do Chapter 6 stuff. If you don't, feel free to ask questions. That's fine. I just can't go over that kind of stuff during the lecture. So for this one, for the positive 1.36, the probability that we get is 0.9131. And for the negative 1.36, it is 0.0869. We get these from the tables, and that gets us 0.8269. So this is the probability that the sample mean is going to be within 1,000 of the population mean on either side. That's 82%. Moving on to B, what is the probability of the new sample mean price for a sample of 100 subscribers is within 1,000 of the population mean? So this is essentially the same problem, except that we're upping the number of subscribers. So we're changing the n value. So I'm just going to go ahead and do what makes this problem different. So the only thing that n affects, right? So we're still looking within 1,000. So that when we go to do our z calculation, or to go find our z-score or our z values, the top part of the fraction is still going to be the 28,100 minus 27,100, giving us a positive 1,000 for one end, and then we'll get a negative 1,000 for the other end. So that's not going to change. What will change is our sigma of x bar, because our sample changes. So our sigma of x bar is going to still be equal to sigma over the square root of n, but now n is different. So sigma stays the same, so it's 5,200, and now it's going to be over the square root of 100, not square root of 50. So that's going to be a nice round number. So it's going to be 5,200 divided by 10. That gives us 520. So now I'm going to just substitute this 520 into the different z formulas. So I'm going to simplify because we know that each one of the z-scores is going to be a positive 1,000 on the top and then a negative 1,000 on the top of the other one. So I'm just going to say this is equal to, z is going to be equal to 1,000 over 520. And this other z is going to be equal to negative 1,000 over 520. At this point, you know that they're going to be the same number, except one's going to be negative, one's not going to be negative. And if we look on the z-table, we're going to get a positive 1.92, negative 1.92. I guess never mind. We don't look in the z-table yet. That's just a calculation. So 1.92, negative 1.92. So then we do the same procedure that we did now right here. And we're going to get the probability that z is less than 1.92. And we are getting 0.9726. And that's going to be minus the probability that z is less than negative 1.92. And that's just going to be 0.0274. And they are then going to subtract out to give us a probability of 9452. What's interesting about this? So now we're saying, what is the probability excuse me, was probability that the sample mean of a new vehicle price of a sample of 50 subscribers is within 1,000 of the population mean. So it's like fairly accurate to the population mean. Okay, notice what happens here. We have a sample of 50 in A, and we have roughly an 83% chance that our sample mean is going to be within 1,000 of the mu, 1,000 of our 27,100. Okay, we increase the sample size to 100, so we double the sample size, and look how much accuracy we get. Now we have a 94.5% chance that we're going to be within 1,000 of the sample of the proposed population mu, right? So this is just trying to illustrate the fact that like we double that sample size and we're getting a heightened level of accuracy on our estimate of mu. Okay. Within what range should the middle 95% of the sample means fall? Assume a sample size of 100. Okay, so this is asking us essentially to do a confidence interval. So the first thing that we need to understand, or the first thing that we need to figure out is, what does this 95% mean? Okay, well, we need to get it to something usable, right? So if we thought about this, we would look at our like a little standard normal curve here, and we'd say, well, we need 95% of the results to be in here. Okay, so that leaves us with 0.025 here, 0.025 here, and then thus we're going to be looking for that 95%. So we're looking at kind of an alpha of 0.05. But this is going to be one of these standard numbers that we look for. And I think we just did that in the lecture, and we came up with that for the 95% confidence interval, z is going to be equal to plus or minus 1.96. Okay, and that's what we confirmed by looking at the table. Okay, so it says now, within what range should the middle 95% of the sample means fall? Assume a sample size of 1,000. Okay, and so then this would be, all right, about that mean, where should we be at, assuming that we have a reasonable assumption of the population mean. Okay, and this is as easy as calculating and solving for x bar in the z formula. So we have plus or minus 1.96. We put plus or minus, and this just signifies that we're actually going to be doing two calculations, one for a plus, one for a minus. You'll know what I mean in a second here. We have our z formula, which is just going to be x bar minus mu, right? So mu is 27,100. And that's going to be all over sigma sub x bar. Now, because we have an n equal to 100 here, we're using the sigma sub x bar from our last part, the 520. If we had a sample size of 75, say, we'd have to calculate like a whole new sigma sub x bar. If we had a sample size of 50, just go up to problem A and look there. Okay, so now we're going to be running two different calculations. Let's run it for regular 1.96 first, and then for negative 1.96. So I'll just multiply both sides by 520. So arrow 1.96 times 520. And I'll just simplify it all the way. This whole thing plus 27,100 is going to equal x bar. So that's how we solved for x bar. And we do that as well for the negative 1.96 times 520. And that's going to be equal x bar in that other problem. And the two numbers that we get are, they create a range for us. So for the positive version, we're going to get 28,019.2, 119.2. And for the lower, geez, my pen's not working, we're going to get 26,080.8. That's going to be our range. It's going to be our 95% confidence interval of sample means falling away from the mean. Okay, I'm going to go ahead and conclude this video because it's getting pretty long. So we're going to conclude this at for learning sample means and using the z-tables. So when we continue, we're going to use the t-tables and then move on from there.